The peculiar properties of water. Water is different since we have talked about the three major types of, or three major examples of hydrogen bonds that we have. And since hydrogen can make hydrogen bonds with fluorine, or there has to be something like made up of nitrogen, ammonia, good example, and then water. Since we discussed this separately in Colin and extended syllabus, we discussed didn't discuss it in much detail, and this doesn't come as a much detailed part in exams as well. This comes as a detailed part, and we won't told you that this only consists of one hydrogen bond. And we discussed this one in detail too, and we said it can make two hydrogen bonds per molecule. So this one has the most extensive hydrogen bonding in the on the planet, and this hydrogen bonding is actually benefiting us in many ways. We're just going to count a few. So to begin with, enthalpy change of vaporization and boiling point. Water has a much higher enthalpy change of vaporization and boiling point, and this is something that I previously discussed, the boiling point. This is due to extensive hydrogen bonding. The rise in enthalpy changes of vaporization from H2S to H2TE. Now, what we are doing over here is that we're talking about the group 6. And since in group 6, we have elements, oxygen, sulfur, selenium, tellurium. So we are talking about making hydrogen compounds with all of these separately, since you'll see all of them with similar compounds over here. And you'd notice that their enthalpy change of vaporization is actually going from a huge dip from water to H2S, since this one has hydrogen bonds, but this one only has a permanent dipole. Then moving on to H2SE and H2TE, let's discuss the reasons. We have discussed a similar case before, so we're just going to quickly go through it. I hope you'll understand it all quickly. So the change of vaporization from H2S to H2TE, this increase is due to the increasing number of electrons in group 16 atoms, 16 to be exact. This doesn't have to be 6. Okay, going down the group, this leads to increased instantaneous IDID forces as the molecules get bigger. If water only had instantaneous dipole-dipole forces, this value should have been much lower, about 17 kilojoules per mole. Now, this value is higher because we have hydrogen bonds, and that one in an extensive portion. Now, boiling point of water is much higher than predicted by the trend in boiling points for other group 16 hydrides. Hydrides, since we're talking about having hydrogen as a negative state in the rest of these. This is something different. We sometimes also call these hydrides, since that is a common way of calling it. All right. So this indicates we need much more energy to break the bonds between water molecules compared with other hydrides of group 16 elements. Again, the reasons being hydrogen bonding. Make sense? Can we move on?
Yes, sir. Yes.
Good. Surface tension and viscosity. Water has a high surface tension and high viscosity. Uh, do you know the meaning of both, or any one of them?
Viscosity, I think it's related to the thickness and viscosity of a fuel or like something like that.
Okay, what about surface tension?
I don't have any idea about that.
Okay, surface tension is usually created in the surface of liquids. Let's say we have a beaker and we pour some water in it. Now, consider the molecule that is on the topmost level. Now, this molecule, as compared to any molecule in between the center, this would be attracted by different molecules over here, 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 like these, right? All of these. But due to hydrogen bond, this would be attracted. But this one would only be attracted from this, and this side, right? There are no opposing forces. You'd notice there are two opposing forces over here, two in this diagonal, two in this diagonal. So we're balancing the forces. So the forces are only balanced in this case, but for these three, the forces are not balanced. So this is known as surface tension, since every molecule is dragged downwards in case of water. Now, when we are talking about falling water drop, you would notice that we usually draw it like this. Now, this is also due to surface tension, that it gets a shape like this. Where the attraction is most, it gets circular. Where the attraction is least, it has a pointy end. This is also due to surface tension. Surface tension is all because of hydrogen bonding. It plays a great role for surface tension. And this surface tension actually causes many different properties in water. Since we are only touching it as a name and we're not discussing the details of it except for this line, right? It causes the surface tension to be higher than most of the liquids. For the surface tension to be higher than most of the liquids, water behaves a little differently. Most of the liquids, when we heat them up or when we cool them down, what happens is that they tend to heat up from bottom, or they tend to start cooling from bottom. Water behaves differently. Since the surface tension is so high, whenever you take something, let's say you take a beaker or you take a utensil, a simple kitchen utensil, you put it in a freezer, you put some of the water in it, and after some time, don't give it so much time that it completely freezes. After some time, take it out, you'd notice that there would be water under, but a layer of ice just on top, which you, if you break, you would easily be able to notice the rest of the water in the liquid form and not frozen yet, right? I hope you have noticed.
Yes, sir.
Good, good. So this is because of surface tension. All the liquids start cooling from the bottom, go all the way to top. Same happens in case of heating. Water is gets heated from the top as well as when we are cooling it, it starts cooling from the top. This is due to higher surface tension than most of the liquids. Higher the surface tension, more are the chances for this phenomenon to occur. Lower the surface tension, least are the chances for this phenomenon to occur. All right.
Yes, sir.
Okay. Moving on. Now, let's define viscosity. Viscosity is actually resistance to its own flow. Sometimes some liquids are in a habit of going with a laminar flow. Laminar flow is when all the particles try to move in straight, simple lines, and we form a good stream of a liquid flowing. If a liquid has a higher viscosity, it tends to move in random direction and sometimes blocks its own flow. We call this kind of flow as turbid flow. This is then known as a turbid flow. This is known as a simple planar or laminar flow. The turbid flow is a phenomenon which is usually shown in fast moving water. You might have seen it with springs that have rocks as their surface, not a flat surface, which have bumpy rocks in them. This usually happens in northern areas of Pakistan. You might have seen similar springs, similar places in the other parts of the world as well, right? Which have this kind of turbid flow with fast moving water. Turbid flow or viscosity can be a little bit related to one another, though there are other reasons to turbid flow as well, but viscosity is one of the reasons as well. So if a thing is too viscous, as you were talking about in case of thickness of liquids, yeah, that is also right. We also term viscosity as a thickness of a liquid. In that case, the flow is going to be extremely slow. For example, take a utensil, put some water in it, turn the utensil over, water will flow out in a fraction of a second. Take the same utensil, pour some honey in it, turn it over, and honey would take some time to come out. No matter how many times you say, honey, come out, honey, come out, honey won't come out. The honey would take its time, right? So it's actually a viscous liquid, right? Get the
Yes,
point?
sir.
Okay, good, good. So that's viscosity and surface tension. You do not need to explain them in paper since they're not a part of your course, but you should be able to count these as one of the factors which arise due to hydrogen bonding. So simply naming them in the paper as a phenomenon that is arised by hydrogen bonding is good enough. But still, we explain a little bit to the students that if they try to make a tangling question out of it, you won't slip. Ice is less dense than water. Now, this is a phenomenon to be properly understood. Most solids are denser than their liquids. This is because the molecules are more closely packed in a solid state than it is in a liquid state. And this goes for most of the solids. This is something that we begin with when we start teaching the kinetic molecular theory to students. But this is not true of water. When ice forms from water, there is a three-dimensional hydrogen bonded network of water molecules. So much so that you would notice that there is an oxygen atom in the center. There are two covalently bonded hydrogen on these two sides. And on the other diagonal, we can safely say there are two hydrogen bonded hydrogen atoms on the other side. So much so, it takes a shape of a tetrahedron in which each oxygen atom is surrounded by four. Tetra means four hydrogen atoms. Two of them covalently bonded, hence single lines, straight lines. Two of them with hydrogen bonding, hence dotted lines. This more open arrangement, which has more open spaces on many of its sides, has relatively long bond lengths due to hydrogen bonding, allows the water molecules to be slightly further apart from one another, since the structure wouldn't end. This would be hydrogen bonded to some other oxygen. This would be covalently bonded to some other. Sorry, this shouldn't be drawn like this, instead like this. So this should be covalently bonded to other oxygen atoms, so on and so forth. So as a whole, the molecules are a little bit further apart. The atoms do the same, and there are empty spaces, a lot of empty spaces, which actually gives less density to ice than of liquid water, which is easily visible in this diagram and every diagram. Every time you are going to pour some cubes of ice onto any of your beverages, cold drinks, or water, you would so see that the cubes would start floating on water, since because of these empty spaces, it has less density than water. And this is because of this tetrahedron. All right. This shape
Yes,
has
sir.
been given in past paper questions. That's why I drew the shape. The similar thing can be observed over here. So actually, oxygen atoms are red, hydrogen atoms are white, hydrogen bonds are lilac, and this is the arrangement, right? Instead, all of them seems lilac. Well, no problem. Colors of pirated book. Okay,
Yeah.
moving on. So bonding and physical properties. The type of bonding between atoms, ions, or molecules influence the physical properties of a substance. Pretty easy, since we have studied that physical properties of ionic compounds and covalent compounds are totally opposite to one another in IGCSE. So this time we have added more types of bonding. We have discussed data bonding. Metallic bonding is something we discussed back in IGCSE. We have discussed some intermolecular forces as well. We have discussed some special cases like hydrogen bonding. So let's discuss them as a whole, but most of it would be something that you have previously discussed at the IGCSE level. So giant structures, ionic structures, or metallic lattices, or specifically the giant molecular structures of carbon in graphite and diamond, or in silica for silicon and oxygen, generally have high melting points, but this does not give evidence about the type of bonding. So these can be considered as a special separate case, especially the giant molecular ones. If a substance has low melting point, it is a better indication that the bonding is covalent within the molecule, and there are weak van der Waals forces or forces of attraction between the molecules. Intermolecular forces, those can be any kind of forces. It can be London dispersion, it can be temporary ID forces, or maybe a permanent dipole, but still the smaller structure or covalent bonding would give rise to lower melting points. All right. So let's discuss a few cases, since the examples would make this topic much easier to understand. Physical state at room temperature and pressure. Ionic compounds. Ionic compounds are solid. This is because they have strong electrostatic forces of attraction. And remember, this is the strongest type of attractive forces we have discussed so far. Since they are in between completely positive and negative ions, so it's the strongest type. Now they are regularly arranged in a 3D lattice. Oppositely charged ions close to one another, fixed in a position, cannot move. and show many of its properties: high melting point, high boiling point, high enthalpy changes of vaporization. Since they cannot move, they do not show any malleability or ductility. They do not even show the electrical conductivity when they are in solid form. And it takes a lot of energy to overcome the strong electrostatic attractive forces. When we talk about metals, apart from mercury, all of them are solids. Many metals have high melting points, high boiling points, high densities, high enthalpy changes of vaporization. This is because a lot of energy is needed to overcome their strong attractive forces between positive ions and sea of delocalized electrons. Many times over, this has happened in past papers, specifically paper 1 for MCQs, that they have considered positive and negative ions for metals. You should be able to see that as an error, as a statement with error, as a false statement, right then and there, because of C of delocalized electron to be a fact for metallic bonding and not negative ions. Remember that not all the metals have high melting points. Remember, group 1 metals and mercury have lower melting points than some non-metals. So do not use high melting point as a characteristic of all metals until you're only referring to transition elements. Or even if you're doing that, try using a safe word. Try mentioning transition elements next to it so that the examiner understands that you are doing it as a right thing and not as a mistake and not as a generic statement. Moving on, covalently bonded substances with simpler structures, for example, water and ammonia, usually liquids or gases, intermolecular forces are weak. It does not take much energy to overcome these intermolecular forces. So these substances have lower melting points, lower boiling points, lower enthalpy changes of vaporization as compared to ionic compounds. Now, some substances have covalently bonded molecules, maybe solids at room temperature. Iodine and polythene are very good examples. These are usually molecules where the total ID-ID forces are considerable since the number of ID-ID forces are huge. All right. So the melting point of these substances are fairly low compared with ionic compounds or most metals. Okay. Now, here I would like to tell you something that most students make a mistake in. Now, when we are going to heat up ionic compounds and when we're going to melt them, we need to break the lattice. We need to break the ionic bonds. When we're talking about metals, the same thing happens. We break, or we tend to safely break the tight packing or the metallic bonds. You can use these words. You will get marks for it. However, remember, when we are melting or boiling covalent compounds, we are not breaking the covalent bonds. Keep this thing in mind. We are only overcoming the intermolecular forces. As soon as we overcome the intermolecular forces, we're capable of changing solid into a liquid. Boom, melting happened, liquid into a gas. There you go, boiling happened. But you never broke their covalent bonds. So since this is not very clearly written over here, they manipulate this for MCQs and for theory questions. You'll see this a lot of times in the questions from this part. Made sense?
Yes, sir.
Good. Solubility. Ionic compounds are mostly soluble in water since they're polar, and now we know the polarity of water as well, being a covalent compound and having hydrogen bonding, ion dipole attractions will happen. Now, ion dipole attraction is something that is a section 19.4. Remember, we only have 18 chapters in AS, so this is something from A2. But we need to still explain them since some parts of AS or some questions of AS require this knowledge. Let me explain. Let's take the most basic example, the salt we are eating every day. We mix it in water whenever we are making different meals. As soon as this goes in water, we say it dissolves. What happens? Now, NaCl is broken down into Na positive and Cl negative ions. But this was ionic bonding. This was the strongest kind of bonding or intermolecular force we have studied so far, or that exists. How come water has the energy to break it down? Any idea?
Can you repeat your statement again, sir?
The strongest kind of bonding we have on this book or on the planet is ionic bonding. This is one of the most strongest types of bonding. Now, in order to break that, in order to break this NaCl or to melt it, even for that, we need 801 degrees centigrade for melting point alone. We're not talking about the boiling point. To convert NaCl into Na positive and Cl negative ions, to break the lattice, we need this much heat. But when we pour this salt in water, we can easily dissolve it in water, break the bonding without giving it that much heat. So obviously there has been some expense of energy. Where does the energy in water comes from? Where does the energy in water comes from to break this strong ionically bonded substance into its ions? Okay, now so every time when there is a bond formed, there is a chemical reaction, there are some interactive forces. Most of the time, the reasons of anything happening is stability. Things, chemicals, atoms, molecules try to become as much stable as they can, and they try to prefer it over their unstable forms. Now, this one is present in a lattice. Though an ionic lattice is strongly bonded, but when it goes into water, what happens is that oxygen and hydrogen are also charged. Though they're not completely charged, but as we have studied from hydrogen bonding, this is partially negatively charged, and both the hydrogen atoms are partially positively charged. What happens is that every time a part of the lattice is broken down, every sodium ion is surrounded by all of the oxygen atoms from from hydrogen, water, and they're all partially negatively charged. All right. And then on the other end, this is chloride ions, and they are also surrounded by hydrogen. So hydrogen tends to surround them, and all of these hydrogens are actually from water, and they surround it. Why? Because they are all partially positively charged. Now, this kind of structure that I've just drawn is usually explained in A2, but I'm explaining you here so that I can explain the word ion dipole attractions. These are ions that broken off from an ionic lattice, chloride and sodium, and these are dipoles which are attracting them. And remember, the opposite poles are attracting the ones. For example, chloride ion is negatively charged and partially positive hydrogen are surrounding it. Sodium is positively charged and partially negatively charged oxygen are surrounding it. Now, what happens or what forms after this ion dipole attractions are more stable than the lattice itself or than this structure itself. So both of them actually tend to go with something that is more of a stable kind of arrangement. What happens? Salt dissolves in water. But sometimes these ion dipole interactions are not more stable than the original lattice. What happens? We call that salt insoluble. It does not dissolve in water. Since the reactions tend to go in such a way that if they move in forward direction, they get towards a more stable structure. So if the forward direction is not taking them towards a more stable structure, they won't move forward. If the reaction doesn't move forward, in this case, in the case of solubility, which actually isn't a reaction, which is a physical change, this attractive forces change. So what happens? We call it an insoluble salt. Makes sense?
Yes, sir.
Good. So metals do not dissolve in water. The forces of attraction between the ions and delocalized electrons is too great for water molecules to disrupt the structure and form bonds with ions. However, some of the metals may react with water rather than dissolving in water. Most of the group 1 elements or the bottom ones in group 2. Covalent compounds, covalently bonded substances with simple molecular structure fall into two groups. Those that are insoluble in water. Most covalently bonded compounds are nonpolar. Water is polar. They're not attracted. They're insoluble. An example is iodine. Those that are soluble in water, smaller molecules that can form hydrogen bonds with water are generally soluble. The examples are alcohols. Ethanol is a pretty great example in that case. Since one of the structures will have oxygen bonded to hydrogen, and the other one would have another oxygen bonded to hydrogen, having lone pairs available. So it completes all the prerequisites for a hydrogen bond. So this partially positively charged hydrogen will make a hydrogen bond with this oxygen. All right. Not in this way, not in such a bad way, poorly drawn way, but it does. Can we move on?
Yes, sir.
Okay. Some covalently bonded substances react with water rather than dissolving in it. HCl is an example. It reacts with water. It forms hydrogen ions and chloride ions. The ions are soluble. Instead of this gas, it forms an aqueous solution of an acid. We call it hydrochloric acid. Remember, hydrogen chloride is a gas. When we dissolve this gas in water, it forms hydrochloric acid. Remember, ammonia is a gas. When we dissolve it in water, it forms ammonium hydroxide, which we also call aqueous ammonia, which is a great alkali, and we have used it way too many times for our different reactions, specifically precipitation reactions. Silicon chloride reacts with water. It forms hydrogen ions, chloride ions, and silicon dioxide. This reaction is called a hydrolysis reaction. We're going to study this reaction in detail, but not yet. It's around chapter 10 or 11. Electrical conductivity. Electrical conductivity in molten or aqueous ionic compounds is due to mobile ions. Electrical conductivity in metal is due to mobile electrons. So ionic compounds are going to conduct electricity when it's molten due to mobile ions, when in aqueous form due to ions are dissolved in water and able to move around freely. But when they are solid, they can only vibrate around a fixed point, so they do not conduct electricity. Metals conduct electricity when solid or when molten because in both the cases, the delocalized electrons can easily move through the entire structure. Or in liquid state because they neither have ions nor electrons that are mobile. However, graphite is an exception since it has some delocalized electrons, so that's why it is able to conduct electricity. Now, we carry easily a practical activity in which we are given separate solid substances. We take a battery, we make a circuit, we connect it to a bulb, and we use some clamps or clips, and we see whether the bulb lights up or not. And we go on with experimenting with liquids, we go on experimenting with solids, we can experiment with some solutions, and we can finally safely find out which conducts electricity and which does not. There are a few questions that you can try to answer and can be very helpful. This finishes the chapter for us.